Hi, hello, and welcome. We're going to continue to do with further dive into Curve's ecosystem. And this was from the result of a previous audit. Some of the issues shared in this file: a temporal ratchet, principal leakage, crushing replay, governance state corruption, and this is really funny. The the AI tool that generated these slides rewarded a number of things. But let's see. First, let's dive into checkpoint logic. This video is centered around where it gets to checkpoints. So looking at this, the internal checkpoint function, it's getting to utilize global, Curve utilizes both global and user states checkpoints. So there's a global checkpoint for the entire system and also the user checkpoint for each user and their specific tokens. This checkpoint function currently takes a token ID, the old locked amount of end time of the user, as well as the new locked amount of end time. Checkpoint is called when there's a change in protocol specific functions, variables, say things like depositing, withdrawing, locking, and unlocking tokens as well. Anything that affects your vote weight and your extreme ability over power over the system. If you see that here, it initializes 2 point variables, the old and the new, to allow easy computation in between the old slope, the new slope, and sets the epoch as well to this local variable because there'll be multiple checks run on that. If there is no previous record of this token, if token ID is zero, if it's spam, then it just runs in here. If it doesn't, then continues down here. It initializes last points to the bias of zero, the slope of zero, and the current block timestamp and block number. It checks if there's any previous history for that epoch. And if there isn't, it gets to set the last point as a read, the most recent point history from data, from storage. Data, storage, memory, all of these things, they would call data that is. They'll come in pretty useful really soon when we find out that you see over here, checkpoint does not memory copy. It was a crazy bug, depending on how this function itself is re-engineered. Now, different protocols get to rewrite this based on how they see fit. And these are just some things to check out for. These are some guides, in a sense, to get to look out for subsequent reviews. Now, here's where it's fancy. Here again, we initialize another point variable. It's a memory variable that can be manipulated during the life cycle of this function, and it's set to last point. But this is not a memory copy. Unfortunately, this is a pointer. So the initial last point is actually giving the last point's memory pointer. That means if you get to read into initial last point, you get the exact same values that are present on last point. And if initial last point is operated on in any way, it will be effectively updating the last point variable. We use initial last point and last points quite interchangeably, but I'm pretty sure you're following along. Block slope set to zero, and it checks that the timestamp, the current timestamp, is greater than the previous timestamp. If it is, it gets to adjust the slope. Now, what this happens, this gets to build the history, calculate what the current point is, and this should happen at least once every 5 years so that the vote weights don't get broken, and also that this for loop doesn't grow too large and then run out of gas. This is some intensive calculation. Let's go through. TI is incremented by a week, and we see that it's first rounded down. And then, so you can expect that for every variable of TI, it's starting at the first day of every week, which is Thursday midnight by these standards. This loop is set to 0, and then it checks if the current timestamp is greater than the blocked timestamp. It brings it down to just set it to the current timestamp. If not, it updates this loop. Just sets this variable in here. The bias, the slope, all of these things are not likely to happen. So it's unlikely that bias, well, it's unlikely that the slope will be less than 0, but it's likely that the bias could be less than 0 because it's an int, not, you expect it to be at values greater than 0. I have a diagram I'll get to show you in a bit. That's in here, calculating the slope of your voting power. So the slope could be negative. The bias rather could be negative, but the slope is unlikely to. Then these values are set. The epoch is incremented, and we move forward to update the state variable of the epoch. If the last point was this block, no point changing anymore. The slope has been applied already. And then it sets the global checkpoint here in point history. The point history is set to the most recent epoch, which was incremented here, and then saved to last point. So last point now is saved into the global state. And then the user history is adjusted here. So the user point epoch for this token ID is set to this, the most recent change. Now we could look into this issue here. It's I think it's not something that's so new, but it's something to get to as well. This is taking some time to load up. Let's see. While that loads up, I'll go through two of these issues here. And you can get to read through the rest when the report is released or this document is publicly available. For this first issue, we're looking at structural weak ratcheting. It's a lot of big grammar, but it translates to a timing mismatch. Now, in the current implementation of this contract, it's possible to split or merge your tokens for your voting power. So you could split the current NFT that's available into two different NFTs, and then you'd split your voting power as well. The ratio determined by you, and the merge also happens the same way. Now, the issue here is that when split and merge are called, there's no check that the locked end time is not bypassed. It's not crossed over. So, say for example, you intended to lock your tokens for 4 years, and because you have this 4-year lock, you expect that if you split or merge or you withdraw or add to this balance, it would all expire at that 4-year timestamp. Regularly, this shouldn't be something that is updated. It shouldn't be something that's changed. But currently, the splits and merge functions get to add another week to the lock duration, meaning that you could say have a 1000 voting power position split into two, 500 and 500, and then your voting power would remain the same even after 1 week elapses because your new locked in time, your slope, the bias is calculated using that end time in mind. Comparing that to the block timestamp, you effectively hold your position as long as you can while retaining the same voting power at the very initial start. So voting power is expected to decay over time. So at the beginning of 4 years, you probably should have 10,000 voting power. At the end of 4 years, you should have zero left. But due to this issue with weekly, yeah, I think I have this here. Yeah, so merge checks the weighted end for the first token and the second token. When you put them together, should that's the weighted value. You don't want your, say, two voting power position to if affect the 1,000 voting power position disproportionately. So the new end is calculated as the weighted end divided by week, multiplied by week. That's it's rounded it down, but also including 1 week. So this new end time allows you to push your expiry to the future. But now every calculation that involves the voting power for that token would be reading nearly the same amount as it previously was. And you could do this every week at little to no cost. So at the end of 4 years, by doing this once a week, you had the same amount of voting power that you started with, and it cost you almost nothing. So you could keep on splitting and merging little side positions to make a full position stay the same. And it's similar for the split function as well. The second issue here was also an interesting one found by my colleagues. For the splits, it gets to double charge the for tokens. Pretty interesting as well, because the create lock function, when creating a new lock, will transfer from the user directly to the new NFT. Instead, you should just get to split whatever you have in the current NFT into two different NFTs. Crazy. So as long as the user who calls split has tokens anywhere, has access to tokens, has approvals, those tokens are what will be sent to the new split. So think of it this way: you have 1,000 tokens in the escrow system, you have 1,000 tokens locked in that NFT, and you intended to split it into two, maybe 500 and 500, but you also are holding, say, 500 extra tokens in your wallet. Instead of splitting the first position into two, you'd be sending your other 500 tokens to a new position that was created. Now, there are three other issues in here that you get to look through. I believe they should be open. Yes. And this was also found earlier. Share memory. Now, initial last point is a pointer which points to the last point instead of a copy. So you could get to read through this issue as well and see how this will get to affect calculations and what.